BOD test. The sample is first diluted with a known volume of specially prepared dilution water. Dilution water contains salts and nutrients necessary for biological activity and phosphate buffer to maintain pH around 7 to 7.5. Diluted water is fully aerated. The initial dissolved oxygen of diluted sample is measured. The diluted sample is then incubated for 5 days at 20 degrees Celsius. The dissolved oxygen of a diluted sample after the incubation period is found out. Difference between initial dissolved oxygen of diluted sample after the incubation period is found out. Difference between the initial dissolved oxygen and the final dissolved oxygen value will indicate the value oxygen consumed by sewage sample in aerobic decomposition in 5 days. BOD in milligram per liter or parts per million is then calculated by using the equation BOD is equal to dissolved oxygen consumed in the test by diluted sample into volume of diluted sample over volume of undiluted sample sewage sample. BOD test. Factor on the right hand side is dilution factor. For example, 1% diluted sample means 1 milliliter of sewage diluted to make 100 milliliter of a test sample, and hence dilution factor will be 100, as 1 milliliter has been diluted by 100 times to make 100 ml, hence multiplying factor would be 100. In actual practice, BOD bottles having 300 milliliter volume is used for experiment. Given volume of sample, say 5 milliliter, is placed in bottle and mixed with pure aerated dilution water to make 300 milliliter diluted sample. Sample is incubated at 20 degrees Celsius for a period of 5 days. Light must be excluded from the incubator to prevent algal growth that may produce oxygen in bottle. Dissolved oxygen. Dissolved oxygen content before and after incubation are determined. BOD of sewage is then calculated as BOD is equal to dissolved oxygen consumed by diluted sample into 300 by 5. Drive equation of first stage BOD. In fact, the scientists here are more concerned with the first stage BOD since oxygen consumed in its satisfaction is not recoverable. Hence, term BOD is usually used to mean first stage BOD, that is demand due to presence of carbonaceous matter alone. Rate at which BOD is satisfied at any time depends on temperature and also on amount and nature of organic matter present in sewage at that time. Drive equation of first stage BOD. Rate at which BOD is satisfied at any time, that is the rate of deoxygenation, depends on temperature and also on the amount of nature of organic matter present in sewage at that time. This is amount of organic matter present in liter. LT is equal to L at T is equal to 0, that is a start. LT, this is L at any time T is equal to 0, time in days decay, time in days T, first stage BOD curve. Thus, at certain temperature, the rate of deoxygenation is assumed to be directly proportional to the amount of organic matter present in sewage at that time. That is, dLT by dt is equal to minus KLT star, where LT is equal to oxygen equivalent of a carbonaceous oxidizable organic matter present in sewage after 3 days from the start of oxidation in milligram per liter. T is equal to time in days, K is equal to rate constant signifying rate of oxidation of organic matter, and it depends upon the nature of organic matter and temperature. Its unit is per day. K. Integrating equation 7.12, we get 7.12 is this equation, dLT by dt is equal to minus KLT star. Then integration dLT by LT is equal to minus integration K into dt, which is equal to ln LT is equal to minus K into T plus C, where C is a constant of integration and can be evacuated from the boundary conditions at the start, that is when T is equal to 0, that is at any start. LT is equal to L, say substituting in equation 7.13 we have ln L is equal to K into 0 plus C, C is equal to ln L. Substituting the value of C in the equation 7.13 we get ln LT is equal to minus KT plus ln L. Then ln LT or ln LT minus ln L is equal to minus KT. Then ln LT by L is equal to minus KT. Then 2.3 log 10 LT by capital L is equal to minus KT. Log 10 then log 10 L then implies log 10 LT by L is equal to minus KT divided by 2.3 is equals to minus 0.434 K into T, using 0.434 K is equal to KD, where KD double star is the deoxidation constant, or more strictly the BOD rate constant on base 10 at the given temperature, is equal to 0.434 K. Then log 10 LT by L is equal to minus KD into T. Then LT by L is equal to 10 raised to minus KD into T. Now L is the organic matter present at the start of BOD reaction at expressed oxygen equivalent, and LT is the organic matter left after T days, which means that during T days the quantity of organic matter oxidized is equal to L minus LT. If YT represents the total amount of organic matter oxidized in T days, that is the BOD of T days, then we have YT is equal to L minus LT. Taking L out of the bracket on the right hand side, we have YT is equal to L into 1 minus LT by L. Then YT by L is equal to 1 minus LT by L, which implies LT by L is equal to 1 minus YT by Y. So in this value of LT by L in equation 7.15 we get, then 1 minus YT by Y, YT by L is equal to 10 raised to minus KDT. Then which implies YT by L is equal to 1 minus 10 raised to minus KD into T. Then YT is equal to L into 1 minus 10 raised to minus KD into T. This is the important equation. YT is oxygen absorbed in T days. That is BOD of T days. The ultimate first stage BOD YT would be obtained from the above equation. Then we substitute T is equal to infinite days in it. Hence Y infinite is equal to L into 1 minus 10 raised to minus KD into infinity. Then Y infinite is equal to L into 1 minus 10 1 over 10 raised to infinite is equal to L into 1 minus 0. Then or implies Y infinite is equal to L. Hence ultimate first stage BOD Y infinite of a given sewage is equal to the initial oxygen equivalent of the organic matter present in this sewage capital L. This is a fixed quantity and does not depend upon the temperature of the oxidation. The value of KD, however, determines the speed of the BOD reaction without influencing ultimate BOD. As shown in figure 7.4, BOD assertion as a function of KD. This is BOD of T days YT. This is time days T. This is KD3 greater than KD2. This is KD2 greater than KD1. This is KD1. This is B1, this is B2, this is B3, this is YA. It is found to vary with temperature of sewage and this relationship. This is BOD assertion as a function of KD. BOD assertion as a function of KD. Figure 7.4. It is found to vary with temperature of sewage and this relationship is ultimately given by the equation KD T infinity is equal to KD 2T star into 1.047 raised to a temperature minus 20 star, where KD 20 star is the deoxidation constant at 20 degrees Celsius. Numerical value varies between 0.05 to 0.2 per day depending upon nature of organic matter present in sewage. Simple compounds such as sugars and starches are easily utilized by microorganisms and have a high KD rate, while complex molecules such as phenols are difficult to assimilate and hence have low KD values. Some typical KD values are given in table 7.2. Then KD T infinity is equal to deoxidation constant and temperature T degrees Celsius. Deoxidation constant KD. Typical values of KD at 20 degrees Celsius for various types of water and wastewaters. Water type, tap waters. KD values per day less than 0.05. Surface water between 0.05 to 0.1. Municipal wastewater between 0.1 to 0.15. Treated sewage effluents between 0.05 to 0.1. Then is the wastewater treatment. Wastewater treatment purpose: to manage water discharge from homes, business and industries to reduce threat of water pollution. Then is the wastewater treatment. Pre-treatment. First pre-treatment in wastewater treatment, then preliminary, second preliminary treatment, third primary treatment, fourth secondary treatment, fifth sludge biosolids disposal. Wastewater treatment. Pre-treatment occurs in business or industry prior to discharge. Prevention of toxic chemicals or excess nutrients with discharge in wastewater. Then is the wastewater treatment. This is incoming raw sewage from sewer line. This is screens. This is grid chamber. This is the here is the raw sewage from sewer line which is transferring. Arrow means these are transferring. Then then this is sludge. Here is the grid chamber. Here is the sludge. Here is the sedimentation tank. Here is the from the sedimentation tanks are the two pipes. Here is the arrow. Here goes to air. This is aeration. This is final sedimentation tank. This is aeration tank. It goes on. It goes like that here. Then goes to digester. Then goes to sludge drying beds. Sludge is disposed of in a landfill or used to improve agricultural land or for mine reclamation. Then disinfection. Then discharge of treated water to surface water, rivers, lakes or oceans. Note here. From incoming raw sewage from sewer line to sedimentation tank is the primary treatment. Then to then air to disinfection is the secondary treatment. From aeration tank to disinfection is the secondary treatment. Wastewater treatment. Preliminary treatment removes large objects and non-degradable materials, protects pumps and equipment from damage, bar screen and grid chamber. Wastewater treatment. Bar screen catches large objects that have gotten into sewer systems such as bricks, bottles, pieces of wood, etc. Wastewater treatment. Grid chamber removes rocks, gravel, broken glass, etc. Mesh screen removes diapers, combs, towels, plastic bags, syringes, etc. Wastewater treatment. Preliminary treatment. Preliminary treatment to remove debris and grit. This is raw sewage. This is bar screen. This is debris removal. Then this goes to velocity slow course. Grit settles. This is grit chamber. This is grit removal. Then this goes to the landfill. Wastewater treatment. Measurement and sampling at the inlet structure. A flow meter continuously records volume of water entering the treatment plant. Water samples are taken for determination of suspended solids and BOD, biological oxygen demand. Wastewater treatment. Primary treatment. A physical process. Wastewater flow is slowed down and suspended solids settle to the bottom by gravity. Material that settle is called sludge or biosolids. Wastewater treatment. Primary treatment. Then primary treatment to remove particulate organic material. This is clarifier. This is when water enters at center and flows but over wire at edge particulate organic material settles constitutes raw sludge. This is clarifier. This is flat and oil float to top and are skimmed off. This is rotating flow. This is clarifier. This is clarified water. This is raw sludge removal. This is sludge treatment. This is composting. Composting to anaerobic digestion. Anaerobic digestion to fertilizer. Anaerobic digestion to methane. Then is the wastewater treatment is the primary treatment.